So, today we're going to talk about fields and forces at a distance. So, in physics, we like it when we can see a direct cause to an action. So, for example, we have this guy that is pushing or pulling this desk to the right here. So, the motion of the desk, we can see where that action came from because we have what we call a contact force. So, he is putting a contact force on that desk because he is in contact with the desk. And so, that's a direct causation for the motion of the desk. Now, if something's not caused by a contact force, we call this a non-contact force. It looks like magic, right? Something is moving, but we don't see anything else in contact with it. We don't know how it's moving. So what we had to do is we had to come up with a kind of idea as to how these non-contact forces work. Now, non contact forces are also called action at a distance forces. And examples of these are the force of gravity, the magnetic force, and the electrostatic force. So, like I said before, we didn't really understand how these things put forces on other objects. So, physicists came up with this idea of a field. Now, when I say a field, I don't mean like a field of flowers, a field of hay, a football field, a soccer field. We don't mean that. We mean a concept or idea that we use to explain interactions and forces that don't require direct contact. So we draw fields represented as lines with arrows to show direction and strength. Now, this is just how we draw fields. Now, obviously, fields are not perceptible with the human eye, but we can think of them as kind of an aura or just an area around an object. And that object creates this field, which when we put other things in the field, they are affected by the field. So our examples here, we have our gravitational field. So if I were to put a mass in this gravitational field, it would be attracted by the force of gravity and it would fall towards the earth like this. And that's denoted by these arrows right here. Now, when we have these gravitational field lines or magnetic field lines or electricity field lines, we show a direction with an arrow, and we also can see the strength of the field. The strength of this gravitational field is going to be the closest when we're the closest to the Earth, and that's going to be where these lines are closest together as well. So when these lines are the densest, that is when our gravitational field strength is the strongest. You can see as we move away from the Earth, they get farther and farther apart. Now, electric field lines, they go out of positive charges and into negative charges. So these examples up top are examples of just one isolated either positive or negative charge. And then also we can have positive or negative charges kind of together like this, which are forming like a combined electric field. And you can see that we have these field lines, and again, they're densest toward the when we're closest to that charge, and they spread out when we're farther away. So that tells us that that electric field is stronger when you're closer to the charge. And also, I like to think of when I think of the direction of the electric field lines, I like to think of it would be the direction that a positive charge would go. So we know a positive and a positive will repel. So that positive charge, if you put it into this electric field here, it will go away from that positive charge. If I put a positive charge in this negative field produced by this negative charge, it will go toward that negative charge. So the electric field lines go out of positive charges and into negative charges. And then last but not least, we have magnetic field lines. And I almost like to think of a north end of a magnet like a positive charge, because you can see that these magnetic field lines go out of the north and into the south, just like they went out of the positive and into the negative. And so since we know that a magnet has a north and a south end, it's always going to produce a field that's kind of circular like this. You can kind of see how it's going out of the north and into the south. Now, if we put a little compass right here in this magnetic field, what happens here is that it lines up with the magnetic field. And on a compass, it's going to actually point to the south end of the magnet. It's going to line up with this magnetic field. And a compass has a north end and a south end as well. And we know that a north is attracted to a south, and then a north would be repelled by a north, and vice versa, south repelled by a south. So that means that the north end of the compass is attracted to the south, so that's why it will point in the direction of these field lines, which is kind of a weird thing because we know that compasses, when we use them, we use them to point to geographic north of the earth. But what that tells us is that geographic north of the earth is actually magnetic south, which is very, very interesting. So again, today we talked about fields and how they are produced by the Earth. So we have a gravitational field that's produced around the Earth by that Earth. We have a electrostatic force, which is produced by stationary electric charges. And then we have a magnetic field that's produced by magnets. And these things are called action at a distance forces because they are able to affect things that are put in their field when they're not actually touching those things.